Good evening, everyone. I hope you can hear me. Am I audible? Am I audible? Hello, guys. Am I audible? Okay. So let us start with the today's lecture. So before that, I would like to show you one video where m- uh, where it is shown how the solid rocket boosters are tested. So this is a solid rocket booster from a Artemis mission, and it is used in SLS uh, launch vehicle, that is the space launch system. So you might have seen at the sides we have two booster rockets, and in the center we have a core stage. So so these boosters have a solid rocket where the propellants are p-band and polybutyl acrylonitrate, and the other one is ammonium perchlorate. Okay, so this video shows how the solid rocket are tested. So as you can see here, so this shows the sectional view, and in the starting we do the ignition. Okay, so as you can see, the surface, the green is getting consumed. So as you can see, the green here, it is getting consumed, right? Okay. Yeah. Okay. So with this, let us start with the today's class. Okay. So we'll start with the problems first. So in today class, we will be discussing problems on liquid rocket engines and some of the problems on solid rockets, solid propellant rockets. So let us start with the today's class. So we have a first question, that we have a liquid rocket booster which uses kerosene as a fuel and liquid oxygen as an oxidizer. Okay, so we have these two, this kerosene as a fuel and liquid kerosene as an oxidizer is proposed to be developed to provide the uniform thrust of 3400 newtons. So the thrust is given as 3400 kilonewton, and it is also given the burn time. So burn time is 168 seconds. Okay, so mixture ratio is given. MR is 2.09, and it is also given the density of LOX. LOX is liquid oxygen, which is 1141 kg per meter cube, and density of kerosene is given as RP1 is a purified form of kerosene. Okay. Uh, okay. Density of kerosene is 850 kg per meter cube, and ISP is given as 2822.55 Newton second per kg. Okay, so yeah, so I've written a note here that RP1 is highly refined form of kerosene, and it has been used in various several rockets. Most of them is used by SpaceX. So they have a Falcon 9 rocket that uses this fuel. So yeah, so it is used which is also the engine name is the engine that is used in Falcon 9 is Merlin engine, and yeah, it uses RP1 as a fuel and liquid oxygen as a propellant. Okay, so let us see what all things it is asked. So it is asked that we have to find the total mass flow rate at the exhaust. So anybody would like to try? Would you guys like to try first? Uh, can you please reply at least? Anirudh, your voice is not audible. Okay, so probably you can try first. I'll give you 5 minutes, so you can try to calculate the mass flow rate at the exhaust. So maybe I'll draw. So this is the Merlin engine, and it has a staged combustion. So this is the Merlin engine. So this uses something known as stage combustion cycle. Okay, so the exhaust that you can see is through the staged combustion. So the part of the fuel and the oxidizer is used to run the turbine, which in turn drives the pump, and which pressurizes your fuel and the oxidizer into the combustion chamber. Okay, so this part is a combustion chamber, and this is your nozzle, and yeah, this is the throat. Okay, so you guys try to solve this first, then I will explain how to do it. Sri Lakshmi, you're not audible. um, 1 minute, let me check the audio settings. Can you guys please speak?
Yeah, can you hear me now?
Yeah, you're audible. Yeah, so you guys try to solve this.
Yeah, so mass flow rate is thrust by specific impulse.
Yeah, you're correct. So mass flow rate through the exhaust is your thrust divided
Uh,
by your ISP, right? So
correct, correct, yeah.
this is 34,000 kilonewton divided by the ISP, which is 2822.55. Okay, so if you solve this, you will get 12045
4, 5.
point 84507 kgs per
Mm-hmm.
second. Yeah. So next is you have to calculate the mass flow rate of LOX and mass flow rate of kerosene. So how will you do that?
Um, Yeah, I didn't understand how to do that because I think there was a similar problem in this week's assignment also.
Okay. So
Yeah.
just consider this part. You have a combustion chamber, and this is a nozzle. So whatever that is coming out has to come into the chamber, right? The conservation of, because of the conservation of mass.
So, sorry, one second, Mr. Nikhil. Are you writing something or are you, because we can only see a fixed screen actually. I'm not
Is it?
sure if you're writing something
I'm
or.
writing. Uh, is it not visible to everybody? So
Mm.
I'm writing. So what do you see? Maybe I'll.
So, I see that you have written thrust and ISP and all,
Huh. After that, it is not
but
visible. Huh?
no.
Maybe okay. I'll reshare my screen.
Okay.
So stop sharing. Yeah. Now it is visible.
Yeah, now you've written something in red, right? Conservation of
Yes.
mass. Yeah,
So
yeah,
whatever
it's
that
visible.
is going out through the engine has to come in, right? So two things are coming into the chamber, that is the mass of the oxidizer and the mass of the fuel, and it should be equal to the mass that is coming out, right?
Correct.
So now this term is known. So we also know the mixture ratio, that is the mass of the oxidizer by mass of the fuel, which is 2.09. So what you can do is, you have two equations, you have two unknowns, so you can try to solve for m oxidizer and mass of the fuel. Okay, try to do it. We will discuss this. So this is, I think, straightforward. This is mass of the fuel, mass of the oxidizer, mass of the fuel is 1. So 2.09 plus 1, mass of the total mass flow rate is given 12045.8. Okay, so with this you can calculate what is the mass of the fuel. So if you solve this, so you will get mass of the fuel as 3898.3317 kgs per second. And similarly, if you have to calculate mass of the oxidizer, just subtract this with mass of the fuel. So you will get mass of the oxidizer as 8147.5133 kgs per second. Okay, so now the third part is, you have to calculate what is the total mass of logs in tons that is stored in the tanks. So you have a two tank, one of kerosene and one with liquid oxygen that is going into the engine. So you have to calculate what is the total uh, fuel that is stored in these two tanks. Okay, so how will you do that? Okay, I'll show you the problem. So you have to calculate what is the total amount of fuel that is stored in the tanks. Okay, so it is straightforward. So you have the mass flow rate that is going into the chamber, and it is also given the burn duration, right? It is given the burn duration is 168 seconds. Okay, so with this you can calculate, the mass flow rate, and it has to run for 168 seconds. So you can just multiply these flow rate values with 168. You will get the mass of the LOX, and you will get the mass of the kerosene. Okay, so if you do that, so
Okay.
mass of the kerosene is mass flow rate into um, yeah, so the kerosene will be 654.9197 tons, and mass of the oxygen will be mass flow rate of the oxidizer into T prime. So with this you will get 1368.78224 tons. Okay. So okay. So there is. Let me add another. Uh, Sorry, there was some internet issue. Okay. So yeah. So this is. Let me add another problem to this. So if it is asked that you have to design the tank size, you have to design, you have to decide what is the volume of this tank. So can you calculate?
So, yeah, I think we have the density, right? So we can use mass into, um,
Right.
we can, the density is equal to mass by volume to calculate the
Correct.
volume.
Correct. So we have. So if we have to calculate the volume of the tanks, so which is equal to the mass. Okay. Let me. So volume is mass divided by the density. So mass of the kerosene. So if for the kerosene it is 654.9197 into 10 to the power 3, and we have the density of kerosene as 850. Okay, so if you calculate this, um, can you please solve this and let me know what is the value? So this is, if you calculate, you'll get 770.493 meter cube, and similarly for oxidizer we have mass of the oxidizer and density of the oxidizer. So density is 1141, and mass of the oxygen is 1368.782 into 10 to the power 3. Okay, so we have so you will get the value as 1191.6336 meter cube. Okay, so any problems on this? Any doubts?
No, it's clear.
Okay, so let us move to another problem where we have a pump fed liquid rocket engine, and it uses methane and liquid oxygen as liquid methane as a fuel, and liquid oxygen as an oxidizer, and it creates a thrust of 3000 kilonewton. and the burn duration is given as 120 seconds. Now what you have to do is and it is given that the uh, chamber pressure is 6. So, okay, the chamber pressure is 6.5 megapascals, uh, and it uses high pressure pumps to pump in liquid methane and liquid oxygen. It is given that oxygen is stored in uh, tanks at a pressure of 2.5 megapascals, and methane is stored at 0.8 megapascals. Okay, now we have the density of liquid methane and liquid oxygen. We have the ISP, we have the mixture ratio. So we have to calculate again the total mass flow rate to the nozzle. I think this is similar to what we have done. So try to solve these problems and we will discuss the answers after we have completed this solution. Okay, so I hope the question is visible to everyone.
Yes.
Okay, try to solve this. We'll discuss once you have completed it. Okay, so I hope you got the answers right. So, okay, so let us try to solve this. So, we have the mass flow rate through the nozzle is just thrust divided by the ISP, which is 10 to the power 3, which is 1090.909. Correct. I hope you all got the same answer, right?
Yeah, you got this.
Yes, sir.
So next is the
Yes, sir.
volumetric flow rate. To calculate the volumetric flow rate, we have to first let us calculate what is the mass flow rate to the engine. So this is mass flow rate to the nozzle through the exit is equal to mass flow rate to the oxidizer plus mass flow rate through the of the fuel. So which is equal to mass flow rate of the fuel mixture ratio plus 1. So if you calculate the mass flow rate of the fuel, you will get as 3. So the mixture ratio is given as 2.26. There will be 3.26 factor, and you will get mass flow rate of the fuel as 334.6346 kgs per second. Okay, so to calculate the volumetric flow rate, you just have to divide it by the density. So volumetric flow rate of the fuel is 334.6364 by 424, which is equal to 0.78923 meter cubes per second. I hope you got the same answer, right?
Yeah, correct. Yep.
78923, and it is mass flow rate total is 1090.9091. Okay, next is the volumetric flow rate of the logs. So this is similar to what we have done. So we know what is the mass flow rate of the fuel. We can calculate mass flow rate of the oxidizer, which is just difference between the total mass flow rate and the mass flow rate of the fuel. So if you calculate, you will get the mass flow rate of oxidizer as 756.2745 kgs per second. The volumetric flow rate, this will be oxidizer. The oxidizer is divided by, we will divide it by the density. So density of liquid oxygen is 1141, which gives you the value of 0.6628 meter cube per second. So this is 0.6628 meter cube per second. Okay, so now they have asked what is the power required by the pump to feed the liquid methane. So we have a chamber pressure of 6.4 megapascals. In the methane tank, the pressure is 0.8 megapascals. So can you calculate the power required by the pump for kerosene? Okay, so do you know any relation which connects the pressure difference and the flow rate with power? So do you guys can you recall any equation which connects the power
Pressure into flow rate. Pressure
pressure
difference.
pressure difference into flow rate, right? This is the work done by the kerosene. So the pressure difference across the kerosene tank and the combustion chamber is 6.4 minus 0.8 into 10 to the power 6 pascals divided by the flow rate of the kerosene. So the flow rate of the kerosene is 0.78923, which gives you the power of 4.4196 megawatt. Similarly, for work done by the by the oxygen pump, which is equal to 6.4 minus 2.4 into 10 to the power 6 multiplied by the flow rate. So this gives you 2.6512 megawatt. Okay. So any doubts on this?
So, yeah, one question on this volume flow rate. So theoretically, what it means is so much, like for example, the volume flow rate of liquid methane, right? So it means that 0.78 meter cube of methane is getting displaced from the tank per second. Is
Ye-
that what it means?
yes. So 0.78 meter cube is getting displaced from this tank and getting fed into the combustion chamber.
Okay, okay,
Okay,
okay. Thank
and
you.
the work that you are doing is just a flow rate into the pressure difference. That is a displacement work. Okay.
Okay.
Yeah. So any doubts on this? Any other doubts? Okay. So let us move to another problem where we have a similar case. The It is given that the we have a liquid rocket engine, and the pump power required to pump the LOX, liquid oxygen, and liquid methane pumps are 2 megawatt and 5 megawatt respectively. So we have to calculate what is the um, total power supplied by the turbine, and it is given that the efficiency of the pump is 0.78, and uh, for LOX pump, and 0.8 for the methane pump. So can you calculate what is the power that is required supplied by the turbine? So there's a turbine which drives the pump for kerosene, and it drives the pump for oxygen. So
So actual power would be 2 times point 0.7, right?
right. So
That
the
is the
actual
actual
power
power.
is 2 divided by, it will be divided, right? Efficiency. Okay.
Yes,
Uh,
sir.
so it will be 5 divided by 0.8. This will be equal to the total power. Okay. So if you calculate this, you will get the value as 9.10714. Okay. uh,
So
so
one question why is it 2 divided by point 0.7 and not 2
okay,
times?
so the efficiency is given as the actual power divided by the theoretical or ideal, at ideal condition, right? So
Okay, okay, got it.
for the okay, okay, for the pump case it will be opposite, right? Because the efficiency in actual case there will be losses, and you will be supplying more actual power and by the theoretical, right? So theoretically it is 2, efficiency is, so actual power that is supplying is 2 by divided by zero point 0.7, right, for the oxidizer, and for the similarly for the fuel it is 5 divided by zero point 0.8, right?
Okay,
So then,
okay.
and whatever you're supplying is just sum of these two energies. Okay, so that's why it is 9 point. 107. So next question is, uh, so up till this point it is clear, right?
Yes, sir.
Okay. So let
Yes.
us move to another problem where we have a solid rocket motor, and it is given that the chamber pressure uh, uh, that the chamber pressure is 8.7 megapascals at the time of burnout, and we are interested to determine the time required for the pressure to decay to 10%. Okay, so of the combustion chamber at the burnout, the characteristic velocity can be assumed to remain constant. C star, it is given that it is constant, which is 1720 meters per second, and gamma is given, which is 0.65, and now the volume of the combustion chamber at the burnout is given as 0.28 meter cube. Throat dia is given as 85 mm. Okay, so this is what it looks like. You have a nozzle, say if you have a nozzle and the propellant is burning. So once it is completely burnt, we will be having some pressure which is known as burnout pressure. So after this, there is no generation of mass inside the combustion chamber. Whatever is there, whatever the flow is there is because of the pressure difference, and eventually the pressure will reduce, and it will be equal to the atmospheric pressure, or the ambient pressure. So this is what in actual condition it looks like. This is one of the study that we did at IISc. We designed a small rocket motor, and we were interested to characterize the pressure, how the pressure evolves during the time. So you can see, we were having this sugar rocket, that is potassium nitrate, and C12H22O11, that is a sucrose. We made mixed these two things, and we were trying to simulate the pressure versus time graph. So yeah, as you can see, the pressure initially was equal to the atmospheric pressure, and it increases to a steady value of something like 1.7 um, bar, and yeah, and eventually it becomes constant, and uh, after that it decays to after this point is known as burnout, and whatever you have get expelled out due to the pressure difference. And yeah, so you after this burnout, you decrease the pressure inside the combustion chamber decreases. So okay, so during the pressurization process, so I the equation that governs the pressurization process is given as dp by dt um, is equal to uh, yeah. So it will be equal to um, RT by V rho propellant burn area P to the power n minus P A throat divided by C star, right? So this part is a generation term, mass generation, and this part is your mass that is going out of the mass going out through the nozzle. Okay, so during the burnout, you do not have any generation term. So the only equation that you're left with is dp by dt is equal to minus rt by v into p, area of the throat, divided by c star, right? I hope this part was there in the lecture, right?
Correct, sir.
Yes, yeah.
Okay, so if you integrate this equation, okay, let us do some manipulations in this uh, term. So gamma can be written as root of rt by c star. Okay, so let us replace rt, and okay, we can also, so p comes here, c star, so v divided by at is known as L star, that is the characteristics length. Characteristic length. Okay, so you have this. If you replace this RT, you will get C star square uh, into gamma square into, and you will have L star. So yeah, so some any questions? Okay.
No.
No. Right. So dp by, so if you integrate, you will get c star by L star gamma square dt. So this will be, okay, we'll integrate from p burnout to, so we're integrating from this point, this is the initial point, and to some pressure, say p, this is a pb. Okay, so this is uh, p by pb, and which is equal to exponential of minus gamma square c star by L burnout into T minus TB. So this is TB to some burnout time TB. Okay, so this is what you get with the equation.
So, so one question. So this ln and this
Okay,
exponential both are there,
no, no,
or
no, 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 sorry. It,
yeah? Okay, yeah.
yeah.
Okay.
So,
And one more question, sir. So on this characteristic length, right? So that is the volume of the port divided by the throat area, right? So
volume of the combustion chamber.
volume of the combustion chamber. Okay.
Yes.
So what is the significance of this? Like, see, it is not the length of the grain, right?
No. Hmm.
Okay.
So basically, it, okay, L star has a significance that say if you have, if you're okay, so what it tells you is, if you are using a say liquid propellant, so basically it is defined for different type of fuels, and also the initial diameter. So when you inject this fuel into the combustion chamber, it requires certain amount of length to vaporize, right, and to burn, right. So so in this process you have to vaporize, and you have to come okay, at, you need atomization, then vaporization, and finally you have the combustion, right. So this L star is the depends on different type of fuel composition. Okay, So yeah, so this is the parameter which is used to model the size of the combustion chamber. So initially we have this for the fuel, and we bap so we calculate eight throat based on the thrust that is required, and with L star and A we can calculate volume of the combustion chamber. So this L star is the experimentally determined. Okay.
Okay, okay. So L star will be always greater than L, right?
Yes. L.
Okay.
What do you mean by L?
Or
For
the length of the grain, or
uh,
both are not related.
no. So L basically for of okay. L depends on your burnout time. Um, right. So whatever we have. So if you have an end burning grain, if you consider this, we have an end burning grain. So your L depends on your burnout time, right? In that case.
Mhm.
So
Okay.
okay, so yeah, L star for liquids it is experimentally determined because it is dependent on uh, the droplet sizing as well as the fuel type of fuel that you are using. Okay, so maybe I do not have more information on this. Maybe in the next class I'll try to explain you.
Okay. Sure.
So okay, coming on to this, let us calculate what is the uh, characteristic length for this rocket. So okay, so this is given.
So, sorry, so one question before that, like on the previous question, right? Like, if you can please scroll down.
Which one? Yeah.
Yeah, where we calculate this P divided by PB, right? So here we don't know P and PB, right? Both the factors are unknown.
No,
Similarly, T
we
and TB are.
uh, okay. TB you can take. Okay, this is a reference point, right? So you can take this thing at the burnout. You can take TB as 0. Right, from this point how much time it will take to decrease your pressure to a certain amount. Okay, so let us consider this. In this case, this is your the point at this thing is your TB. Okay,
Correct. Yeah. Yeah.
so if it is not given you can take this thing as 0, and uh, yeah, whatever time that you will get will be in reference to this point.
Oh, so the time taken to reach the 10%, whatever is that P,
Huh.
that is the unknown variable. Then that will be T, which will be calculated.
Yes.
Okay. Okay.
Okay.
But then what about the pressure? Because both these pressures are not known, right? Or are they?
Okay, so initially the okay, so it is known it is given that the chamber pressure 8.5 megapascal it is given, which is equal to PB, the time of the burnout.
Oh, okay, okay. So what the question here is to calculate the P.
No, the calculation the question is to calculate the time it requires to reach the chamber pressure of to reach the chamber pressure should reach 10% of this PB. So we have P by PB as 0.1. Okay, sorry, this is 1 divided by 0.1. So this is given, and you have to calculate what is T minus TB. So it is asked what time it takes after the burnout has happened, right? So at the burnout you can take this thing as 0, that is the reference value. At TB the burnout has started, and what delta T is required to reach the pressure of 10% of your uh, burnout, the chamber pressure at the burnout. Okay.
Okay, okay. So the P value is 10% of whatever is given as chamber pressure, right? It is
Yes.
8.5. So
Yes.
that will be 0.85. So P is 0.85 and we'll be calculating T using this equation.
Yes.
Okay, okay.
Okay. If you guys can try to do this, so I'll give you 5 minutes, and after that we'll discuss this.
Yeah, hello.
Yeah.
Yeah, I have one more question. So when Sir had explained this in the lecture, the this equation was actually oh, sorry, no, I think I'm referring to something else. But should this be referred to in terms of the non-dimensional pressure or just the actual value of pressure?
No, this is the actual value. So nowhere
Actual
we have
value.
in this equation, nowhere we have non-dimensionalized the equation.
Okay, okay.
So I
So,
think when professor was telling, so I think they we have non-dimensionalized this thing with, I think S. I think this term we have non-dimensionalized, right? So this is SB rho P A C star divided by A throat, right? We have used this term to non-dimensionalized pressurize, right? So we
yeah,
were
I think
getting
so.
Yes,
this
sir.
this term, right?
Yeah. So you're writing something? Sorry, the screen is frozen, I think.
I am writing. So
Okay.
is it not visible?
No, it's frozen.
Okay. Now.
Not yet. Maybe if you can reshare, stop and start the screen sharing.
Okay. Okay, it's not sharing, huh? 1 minute. I hope it is visible now.
Yeah, yeah, screen is visible.
Okay, so coming on to your question, Shri Lakshmi. So the L star basically tells. So if you have a larger L star, so you we can say that uh, the chamber is okay. Um, what we can say is we have sufficiently long chamber such that the complete combustion can take place. Okay, which in turn tells you that the ISP for that rocket will be higher and the thrust will also be higher. But we cannot have very long engines because that will have a problem with uh, the the mass of the structure that is we are adding into it. So there has to be a optimum length which we specify, that is what known as L star.
Okay, okay, yeah, okay, understood.
Okay,
So L star is calculated through experiments.
experiments, yeah.
Okay.
Okay, so let us try to solve this. So the characteristic length basically is this L star is volume divided by the area of the throat. So the volume is given as 0.28 divided by the throat area, um, which is 85. So 0.085 square. So if you calculate this, um, you will get the value as 49.3435 meter. Okay, so I hope you are getting the same answer, right?
So what is it? 0.25 in the pi?
It is the diameter, so pi by 4 d square.
Okay.
So this is, so is it the throat area, right? So the diameter is given.
Okay.
So this is pi by 4 d square divided by the volume. So this is L star. Okay.
Okay. Okay.
Yeah. So next is the time required. That is um, ln p by p bar is minus c star gamma square by L star t minus pb. Okay, so it is given that it is 0.1 minus c star. Okay, c star is 1720 divided by L 49.3435 0.65 t minus t burn. So if you calculate the t minus t burn, you will get as 0.1563 seconds. Okay, so basically it takes 0.1563 seconds to reach to the 10% of the value. Okay, yeah. So any doubts on this? No? Yes?
Understood.
So let us
No.
try to look into another problem, that is on solid rocket propellant. So, okay. So consider a case where we have a solid rocket um, engine, and we have a grain. So initially it is given that it has a square cross section. Okay, so square and the length is given as 0.4 meter, and the nozzle throat diameter is given as 60 mm, and the length is also given, which is 2 meters. The outer diameter is given as 1.2 meters. Okay, and this is 0.4 meter. Okay, yeah, and the burn rate law is also given, which is equal to 0.0123 p to the power p to the power 0.3. Okay, so density is given as meter cube, and C star is given as meters per second. Okay, so first of all, what it is asked is the initial equilibrium pressure. Okay, so how will you calculate the initial equilibrium pressure?
Sir, by using that SP dot K
Okay, so
formula.
basically what you have to do is the mass balance, right? So whatever we are burning through the surface, okay, that is getting expelled from the nozzle, correct? So whatever you are burning at the surface is going out through the nozzle. Okay, so whatever you are burning is given as density of the propellant, initial burning area, and the regression rate, right? So this is initial pressure, and that will be equal to initial pressure, so AT divided by C star, right? So this is what you are generating, and this is what it is leaving through the nozzle. Okay, so density is given as 1700. Now you have to calculate what is SB. So your SB is given as yeah, So this is 0.4 into 0.4 into 3 p to the power 0.3, and you have p into area of the throat, that is pi by 4 into 0.06 square, right? And divided by the c star. C star is 1600. So if you calculate p equilibrium, you will get,
Sir, burning surface area will take length also, no, sir?
oh yeah, yeah, this is, you're right, correct. So this is
4
equal
into.
to 2 times okay, the perimeter, right? Okay,
Correct,
first
sir.
of all, the perimeter, right? So this is 4 times 0.4 into 2. Is that correct?
Okay, sir, correct.
Correct now. So if you calculate this, you will get the value as 3.47 into 10 to the power 6 pascals. Okay. So next is, you have to find web thickness. So can you calculate the web thickness? Can you calculate the web thickness? Okay.
Yes, sir.
So your web thickness will be equal to the closest this is web thickness.
So I have one question related to this one.
Huh.
In one of the assignments, I think in the last assignment, the wave thickness was given as twice of this number. Isn't it wrong?
Web thickness is given as,
In the assignment question, the port is of circular cross section,
hmm.
radial burning, radial burning solid rocket. The port was given as twice of, yeah,
So you have
twice of,
this thing, right?
yeah, exactly.
Okay. So
Yeah, I too had the same question. So I think to Kabir's point, right, like the inner port diameter was given as 0.1 meter and the outer diameter was given as zero point 0.8.
Yeah.
And the question was what is the web thickness, and the correct answer was given as zero point 0.7.
It's twice of the correct answer was given as the correct answer.
so the web thickness will be equal to 0.7 now. So web thickness is your this distance.
But okay, let me see. Just give me a second.
Huh. So this is the web thickness is your closest distance to from the initial grain surface to the wall. So if you have a star grain, so, okay, if you have a star grain, so whatever the closest distance to the wall is your web thickness. Okay, in case of circular thing, if initial uh, this thing is given 0.1, inner diameter is given, and the outer diameter is 0.8. So the web thickness will be equal to the difference of these two radius.
So, but this point 1 and point 8 are the diameter, right? So the radius would be
You're
half.
yeah,
It is the
you're considering
diameter
it
or
as
the
a
radius?
radius. Yeah, diameter. In the question, it was given as diameter.
Okay, diameter. Huh?
Yeah, diameter.
Okay, then it will be 0.35.
But the answer given was 0.7.
How is it? I'm not sure about it. Maybe you can raise this query, because I am a TA for this course and the people who make the assignment are different. So
Okay.
okay, so
Okay.
yeah, so you can probably raise whenever you have this. I think weekly you get this. You have to fill some form, no?
Feedback form, sir.
Feedback form, right? So there you can mention these problems.
Okay.
Okay, so if okay, so let us calculate the web thickness of this problem. So okay, so the diameter is given as 1.2 meters, right? So the radius will be equal to uh, 0.6 meters minus this distance, right? This distance. So this will be equal to, this is b by 2 and this is also b by 2. So this will be equal to, okay, this will be equal to under root b square by 2 square minus b square. So this is 0.6 minus 1 by 2. Okay, so you have 0.6 root minus root b. If you calculate this, can somebody calculate? Probably you will get the value as 317 meters.
So it's b square by 2 square plus b square by 2 square, right? I mean,
Yes.
calculating the length of the
Yeah, it's just a
hypotenuse.
Pythagoras theorem. So you have a square, you have to calculate this distance, right? And this is your b. This is your b. So this is b by 2. This is b by 2, and to calculate this distance, it will be this b by 2 square minus
Can
b.
we directly calculate the entire diagonal from one vertex to the opposite corner, opposite vertex? Will it be a little simpler?
Uh, yeah, you can calculate, no? This is, and then you take it the half. You'll get the same answer. Okay.
Yeah, yeah.
Okay. So if you calculate the web thickness, you will get the value as 0.317. Okay. Now let us the third problem part is to calculate what is maximum burning surface area. So when this has burned completely, so this will look something like this. So this is our initial surface. So so finally it would have looked like this. So this is your web thickness, right? Not- okay, my drawing is not good. Let me try to make it again. So this is your sliverage, right? And this will be your maximum surface area. Okay, now this is your, from this point this is a web thickness, right? So the perimeter, so the surface area will be equal to the length into the perimeter, right? Whatever perimeter that is left at the burnout. So if you calculate the perimeter, you will get as 4b plus 2 pi into the web thickness, right? This will be your surface area, right?
2 pi because 4 into pi by
So
2,
yeah,
right?
so this is the quarter circle, right? So
Yeah.
we have four such things, so it will be a complete circle. Okay, so if you calculate SB, you will okay. Can you calculate SB? Okay, L is given as 2 into 0.4 plus 2 pi into 0.317. Okay, so
7.18.
okay, so let me use this calculator. Maybe I'll not use it. Okay, no. So this is 7.185 meters square, right? Yeah, you're right. So next is you have to calculate the uh,
In the previous expression, 0.4 into 2 into 0.4 or 4 into 0.4?
where, oh yeah, okay,
In
you're right, this is 4 into 0.4, right?
Yeah, the
So
answer remains same.
okay, anyways, so now you have to calculate sliverage. Okay, so this will be equal to the mass of these four blocks, right? So let us calculate the first the area of this white surface. 1 2 3 4 5 6 7 8 9. Okay, so 1 1 5 okay, this 3 and 8, right? It will be the area will be equal to web thickness into B, right? This is the web thickness and this is your B, correct? And we have four such blocks, so into 4. Then we have pi into WT square, right? So this is a quarter circle, and this the area of a circle is pi r square. The radius is WT. So they will, therefore the total area is pi WT square, right? So can you calculate? And this will be okay, this is your area, right? And if you multiply with the length, you will get the volume. And if you multiply again it with the okay, 1 minute. So this is okay, let us calculate this area first of all.
So, sir, one question. This pi WT square, there are four such things, right? So shouldn't we
Yeah, so
multiply that by four?
this is a quarter circle, right? So this is WT into B into 4. This part is clear, right?
Yeah, that
So
is
this
clear.
is WT square by 4. This is a quarter circle, okay, into 4, because we have four such blocks, right? 2 4 7 and 9.
Okay. Okay.
Makes sense, right?
Okay.
Yeah.
Okay. Yeah. Got it.
Okay.
And
So
we have. How about six? Blah.
6, 1, 2. Oh, okay, you're right. Yeah, yeah, yeah. One
No.
more thing, right? So there will
Four
be,
B.
yeah, there will be b square.
B square. Okay. Yeah.
Okay. Next is you have to calculate the area that is left here. So that is
0.98
this is 0.98.
total. Yeah.
Uh, did you included this b square?
Yeah.
Okay. Let us see this. So I'm just writing the complete equation. So this is so okay. This is the area, right? And this is the volume, and this is the density. So if you multiply with the density, you will get the mass of this leverage, right?
How the d square came, sir? D square L and density.
Okay, this is the area of this surface, right? Whatever blue that you are seeing here, that is the area.
Yes, sir.
Okay, if you multiply with the length, you will get the volume,
Okay, sir.
and if you include the density, you will get the mass. Okay, so calculate this and tell me the final answer.
Sir, that small portion is an area or volume, sir?
Which one?
Beside one, there is a half circle like that.
Can you tell me the number? Probably
One number one, sir.
number one. Okay, this is formed by this surface residing in this direction. Okay, and it will reside up till this wt.
Okay, sir.
Okay, then you will have this wt into b, which is this one area. Okay,
Yes,
so
sir.
this
Yes, sir.
is
Okay.
1 comma 3 comma 5 comma 8. Okay, and this is 2 comma 4 comma 9 comma 7, and this is your 6.
Yes,
Okay,
sir.
yeah. So
Odd and even, sir. Okay.
What is the density?
density, yeah, density it is given as okay, sorry, density is 1700. Okay, 1 minute. So I think we it should be 4, right? Pi d square by 4 minus b square wt square or letter b. Yeah, I think now it is correct, right? Let me also calculate this.
Sir, of 4 came, sir. Pi d square by 4.
This is the area, right? This is the total area, and we are subtracting this is the sliverage area, right? This is the area that is burnt. This is the burnt area. This is the total area enclosed by the circle. Okay, this complete circle is pi d square by 4, right?
Yes, sir.
Okay.
The answer comes out to be around 503 kilogram, I guess.
Point something.
0.46.
Okay, yeah, right. So and let us calculate what is the total mass, initial total mass. So this will be uh, Okay, this is pi by 4 d square minus b square into length into density, right? Can you calculate what is the total mass? It should come something around 330. So if you calculate, you'll get 330.1. So this
Yeah,
is,
same.
so let us calculate what is the
This kilogram, no? Kilogram per, not
oh,
per
sorry,
second.
sorry, yeah, it is kgs. So let us calculate what is the percentage leverage. Okay, so that will be 503.
So what's the value of small b square, sir?
Small b is your this, right? This is 0.4.
0.4.
So with this you will get something around 15%, right? So which is huge. So therefore these type of this type of uh, this type of grain geometry is very less. This is not practically used in most of the engines. Okay, so the most common type is your radially outward. Okay, and the star geometry. In this case, the can you calculate what is the leverage mass in this case?
It
Zero.
should be zero, yeah.
It will be zero, right? Because at the end the complete surface is getting burnt. Okay, right. So um, yeah. So any doubts?
In case of radially burning inward, let's
Huh.
say,
Huh.
the rate of burning will gradually decrease, right?
Rate of burning will gradually decrease. Yes.
Is there any practical use of using this kind
No.
of
In
grain?
practice, you will not be able to realize this type of engines. So can you tell me how are you planning to ignite this surface? It is difficult, right?
Yeah, the entire surface has to be burnt.
Yes, from the outward towards the inward, and even the radially outward propagating grain, burning grain is practically in use because uh, as you cross a certain altitude, your drag reduces and you want to accelerate faster. Okay, so after some time, the pressure will increase and therefore the thrust will also increase. Okay, so they are commonly used.
So there is also a possibility of using different grain configurations at different lengths of this,
Yeah,
like after a particular length.
it is
Yeah.
possible, yeah. So maybe in the beginning, maybe I've shown you a video. So let me.
Is it the space shuttle SRB?
Yes, it is SRS. Yeah, SRB rocket uh, motor
Okay.
for
Okay.
the Artemis mission. So as you can
Okay.
see here, the surface is getting burned, right? You can see, yeah. So this is how the solid rocket motors are tested.
Have
In
they made that particular area transparent, or it is just for
so
it's
yeah,
an animation?
this is they have made a animation. So yeah,
Okay.
they
Okay.
have the whatever you are seeing at 1 minute. So at this point, as you are seeing here, this is the animation. Okay, so you can see at the inlet. Okay, yeah, you can also, okay, so you can have this different type of geometry at certain length and different geometry at, so at the beginning you can have different cross section, and at the other uh, length you can have different cross sections.
Okay, okay.
Okay, so yeah, it is possible. Okay,
Can
so
you discuss a little bit about this so-called phenocyle, conical
yeah,
geometries?
phenocell and
They are a
conicell.
little complex compared to star geometry.
Yeah, right. So I think the, one minute, let me open my notes actually. This is alright. So alright. So maybe I'll tell you different type of grain geometries that are used. So okay. So uh, this is let me start with the end burning grain. So first we have end burning grain. I hope this everybody knows, right? So we have the surface that burns without any change in the area, right? So
Right.
next is your tubular grain, or we also known as readily burning grain, right? Okay, so in readily burning grain you have a structure something like this, and at the, so it is something like a readily, okay, this is readily that is propagating outward. Okay, so next is and next is the star grain geometry. Star grain, which is something like, okay, this is a star grain. Then you can also have star square grain. This is something like this. Okay,
Look like gear. So
huh?
it look like similar to gears.
Yes. So we also have wagon wheel, which is something similar to, then we also have dendrites. Okay. Next is uh, rod and tube arrangement. Okay, where you have propellant, somewhat like this. Okay.
This one is used, I guess, in real rockets.
um, yeah, they all have being tested to some extent, but
Okay.
probably most commons are your star grain and your your tubular grain. Okay, then whatever you asked is your uh, phenogel and conogel, right?
Yeah, phenocell, fin
Okay.
and cylinder, and
Hmm.
cone and cylinder.
Okay, so this is conocell is. Okay, it is something like this.
Sir, sir, can I explain what is phenocellus, conocellus?
Hmm? What?
Can you is explain a little bit about the phenocellus and conocellus?
Okay, this is conocell. So instead of the burning only in the radial direction, it can also burn in this direction, right?
Yes, sir.
And
Yes,
we
sir.
also have so this is the geometry can vary depending on the your mission requirement. So what time, what thrust requirements you need, based on that you can design your own grain geometry. Okay, and so there is a big research area on this. How do you optimize your grain geometry based on your mission requirement? So this is a field in itself. So another is
Uh, is there any use of changing the direction of burning, like in the longitudinal direction instead of radial?
I do not have an idea on this. Probably
Okay.
in next class I'll read about it and let you know. So
Okay.
Okay,
in a
sir.
phenogel
Okay, sir.
you have grain
I think it is seal. CYL.
Sivila.
Yeah, cylinder, fin and cylinder.
So we have something like this. Okay.
What's the difference between sir phenocell and conocell?
Okay. So this is something like a conical thing. Okay. Uh, if you rotate this geometry, so it will become like a cone, no? Cone and a cylinder, and this is a cylindrical grain. Okay. Okay. To be honest, I do not know the purpose right now where they are used, but in the next class maybe I'll read about it and let you know. Okay.
Sir, based on requirement only, sir, they can use. This one is when we pressure initially required high thrust, then they want to,
Yes.
minimum pressure. That time they will use this one.
Yeah, that's what it is. The most of the grain geometries are probably is because of the
Mission
mission
required.
requirements. Yeah, and another one is this is dual first. That is, so in one part you can have, so this part you can have end burning grain, and this part you can have radially outward propagating flame. Okay. So in two cases you will initially you will get progressive burning, and later the thrust will become constant.
Okay, neutral burning, yes, sir.
Huh?
Neutral burning. After that.
After that, it will be neutral burning. Okay. Uh, yeah. So whatever geometry that is, so there's a guideline for designing a solid rocket motor, that is your geometry is decided by pressure time diagram, which in turns is related to your thrust time diagram. Okay. Next is we have to avoid erosive burning, and next is avoid propellant leverage. Okay. Fourth is internal cavity should not cause combustion instability. And fifth one is center of gravity should be as low as possible. Okay. So these are your some of the guidelines which are taken into account while you design a solid rocket booster.
Sir, I have one doubt, sir. Sir, avoid erosive burning. Na? What are the precautions you take, sir? Any idea?
Erosive burning, say if you have designed some kind of uh, rocket engine, and what happens uh, when the part of the propellants are burned from this end, they travel upstream, right? And
With
while
velocity.
traveling they also have some velocity, due to which they
Correct,
create
sir.
some shear force on the surface, right? If you have designed
Correct,
this
sir.
some type of fins, something like that, and
Then,
with this flow it does not burns along the surface, while it just comes out like a chunk, right? It can, what it can do is it can block the nozzle, and eventually it can create high pressure and your motor can explode.
okay. Sir, any relation is there, DVL ratio, anything for this one?
uh, no, I do not know as such, because d by l, no, I don't
Uh,
think is
L
there.
by D, L by
yeah,
D.
yeah, sorry, L by D, L by D, sir.
Yeah, I currently I do not know about this. Probably in the next class I'll try to answer this.
Actually, diameter is varied along the length in order to change this erosive burning behavior.
Okay, sir. Next class I will ask, sir. I have doubt. Okay.
Okay, so any doubt till now? And another one was
Sir, can you explain it?
there is another one, that is the
Is it
cruciform. So this is this. Okay.
Sir, can you explain the dual thrust
Okay,
again?
so dual thrust, say initially if you want a higher burning area, okay, in turn you need a higher pressure or the higher thrust. So what you can do is you can have a first the radial burning surface with some say at this part you have some star grain, okay, star surface. And so yeah, this is one of the geometry that people can use at certain, for certain time you will the thrust profile will be different because of this radially burning surface, and after some time it will become constant because of this end burning, neutral burning. Okay, so you can have different profiles. So my point is you can decide the geometry based on your thrust requirement. Okay, so this whatever geometry that is there can be optimized based on your mission requirement.
The star can have different number of vertices also, right?
Yes, yes, it can
It
have
is
n
not
number of
necessary to be
vertices.
6.
Yeah, so yeah,
Okay.
it can have n number of vertices in practice. Yes.
Till now we are using 13 maximum, sir.
Probably because if you go to a higher large number, it might break, right? Your the strands will be very weak. Okay.
Okay.
Yeah. So there is some. Um, so yeah, sliverage. Basically, we were talking about sliverage. Yeah, no. So whatever I was telling you about this is, let me give you some other part. So so this I am writing the percentage of neutral burning, and this is your grain type. So with end burning you have 100% neutral burning, right? With slotted you have 50 to 90% of neutral burning. So basically what I'm telling here is say if you initially the pressure may increase, then after that you can have a constant pressure, that is known as the neutral burning part. So with slotted grain geometry, what percentage you can, what percentage of neutral burning you can expect. Okay, so slotted can give you 50 to 90%. Then star shape can give you 30 to 60%. Okay, then we have conosyl. This can give you 50 to 90%, and phenosyl is 70 to 90%. Okay, a wagon wheel can give you 10 to 30% of your neutral burning. Okay, yeah, right. So any doubts on this? No. Okay, let me.
Yeah, I had one question actually on this week's assignment.
Hmm.
So one of the question is asking for the average chamber pressure, and there is one more question where they have asked for average burn rate. So by average, do they mean the average between the web burning time, like when it is propellant is actively burning? That one, right? It should not be calculated from ignition onwards, right?
Uh, okay, average when we talk because your burn rate will eventually change, right? Depending on the pressure, if with pressure and the grain surface, grain geometry.
Uh-huh. Correct.
So if you have a the neutral burning, your pressure is almost constant throughout their. uh, burn time, right?
Yeah, I think this is for progressive burning.
Okay, progressive, then I think you have to integrate and divide it by the burn time, probably. So
Oh, okay,
yeah,
okay.
that is the average, right?
Okay, okay.
So probably what we should do is 0 to t burn r 1 upon tb into dt, right? So yeah, so yeah, you have to you have to integrate this over a time and divide it by the burn duration. So actually, to be very honest, I have not seen the assignment. Yeah. So okay.
Uh,
Okay, okay, no problem.
in the
And what
expression of
what next?
R,
What
which
you
of
can do is you can also take this thing as so this is ri. This is r naught. You can take a mean radius and you can calculate based on that.
Okay, okay. Yeah, that is also a feasible one. Yeah.
Yeah.
so the integration need not be calculated.
You need not to calculate. Yeah. So the mean you can calculate based on this mean radius.
Okay, if we simply consider the integral in the this expression for R,
Huh.
which of the quantities will be independent of time?
Yeah, so first of all, your R will depend on the area, right? Instantaneous area. It will depend on the
Yeah,
pressure, right? And
right.
this pressure will in turn depend on your area, burning area. So first of all, if you have to do it in a proper way, detailed way, this AB burning area, you have to calculate the expression for this. So the how this burning area is changing with time. For end burning grain, your AB is a function of time and is given as AB is equal to say
For end burning, it will be constant, right?
for end burning it will be constant. For this
Radial,
radial
radial
grain
by.
it will be uh, this is this is 2 pi r initial plus dr by dt, which is a burning rate, right? And yeah, into uh, your time, whatever time you have, right, into the length, correct? So this is your initial area, and in with time this will increase, right? 2 pi
Right.
ri into dr by dt is a this regression rate, and into t into l. Okay, yeah, this in turn will depend on a pressure, and this pressure again will depend on your r naught. So probably what I would suggest you to do is just take a mean radius and just calculate based on that.
Okay.
Okay. Yeah, that seems to be the easiest one.
Yeah. So
No.
uh, okay. Anything else?
Yes. Hi. I have a doubt. It is not related to this lecture, but related to nozzle design performance. Can I ask?
Please go ahead.
Yeah. So I was actually designing a nozzle. Um, so in order to calculate the in start transient and in end transient, meaning during the my chamber pressure is getting built up, how my impulse is getting generated, and when I close the valve, how it is getting when valve I closed, how the impulse is getting dropped, like thrust. I mean thrust.
Okay.
Okay.
So
So
so huh.
initial time, initial time, what the nozzle has been designed for the 0.2 bar at exit, but I will be test it in the ground. Okay, at sea level test. So what happens, because my initially my chamber pressure is getting built up, I am getting CF negative. So is it the limitation of that formula what we derived, like that 2 gamma square by gamma minus 1, that entire momentum term plus PE minus PA by PC into area ratio? Because my PE is less than PA and my PC is very low, so I am getting a negative term. So that is my doubt. Is it the limitation or is there any other way?
No. So whatever that you are seeing here is having a limitation that you are assuming that your nozzle is choked,
Yes, yes,
right? So at
yes.
initial part, your pressure, whatever whatever you see here, no. So this is what we have written in-house code for our purpose. So what we are doing is we are assuming that the initially the propellant is burning, and we are not assuming that nozzle is choked. Okay, whatever the flow is happening is because of that pressure that is getting increased. And so this is just we can apply Bernoulli, right, when it is incompressible right now. Okay, so once the nozzle is choked, you cannot your the flow that is going inside the outside the nozzle is now limited to your P.
No, actually, my case is it is the I am designing for the liquid propellant, not this one.
But the concept is same, no.
Yes, yes, yes,
So whatever you are supplying, the mass that is inside the engine has to leave through the nozzle. So instead of this term, the generation term, you have mass of the oxidizer plus mass of the fuel,
yes, yes,
correct? And
yes,
instead of this, this will remain same.
yes.
So what is the problem that you are getting?
Because in the CF, I am getting actually initially my CF term I am getting negative. That is why I am getting the negative thrust. Because my thrust when I am calculating F is equal to PCAT into that CF term. And because my P it is designed for the less than my ambient pressure 0.2 bar,
Hmm, hmm.
and my PC is low, that PE minus PA by PC, that term is coming itself higher. And
So how
I mean
are
in
you
negative I am
calculating this
getting,
thrust?
sorry.
How are you calculating this thrust and CF? So CF you are
Yes,
calculating based on this, right?
yes, CF I am calculating, that formula is there, na, that 2 gamma square divided by gamma
Yes,
minus 1.
correct.
Yes, from that formula only. Now my PA is 101325. I am subtracting that from the PE, which is 0.2 bar. So it is giving me now negative term. And since my left side term, that is square root term, is very low, so I am getting CF is negative.
So okay, So let us look into the equation for CF.
Yeah.
So your CF is right, this part, right? No. So we just have to divide it this thing by. So this is your CF. If you
Yes.
divide it by P naught AT,
Yes.
correct? No.
Yes. Yes. Yes.
So which term you are getting as negative? This part.
That right side PE by PC. You have written na PE minus PA by PC A into AT.
Yes.
Yes. This term I am getting uh, in
As
negative.
okay. How are you calculating this P exit?
Uh, P. See, I have assumed this PE I have known na, like when I designed the nozzle,
Hmm.
that PE I know.
No, P will change, no, depending on your stack. So if you have a nozzle, if you have a chamber, so if you have this nozzle, so
Yes.
the P exit will depend on your this stagnation pressure and what is your
Okay. I got your what you asked. That I am calculating on the basis of there was one expression I derived. I just said the moment I close the valve, whatever the mass inside the chamber, that was PCAT by C star. Now the rate at which it is leaving is d by dt of rho into VC. And when I derived it fully, I got an expression. Uh, 1 second, I'll tell how. I got it is varying according to e power minus RTC by C star L star into T.
Okay, I think it is difficult for me to just think. Well, you can share the calculation. Maybe I'll have a look. If I find any problem, maybe I'll let you know. Okay.
Okay.
So
Yeah. Yeah.
because this thing will depend on totally on your nozzle design.
Okay.
Okay. So whatever, say if you have, okay, let us say a very simplest thing, that is a CD nozzle.
Hmm.
That's not CD nozzle. That is a converging nozzle. So if you have a
Hmm.
converging nozzle, and you have a exit, and this is your a inlet, right? So what we do is, so okay, so initially when the pressure is getting built up, and we do not assume that this part is choked, okay, we can apply Bernoulli, right?
Yes.
Or yeah, so or we can use any this gas dynamics relation. Okay, so yeah, 1 minute, let me answer this question. Okay, I'll share my email ID, so if you have any doubts, please. Okay, yeah. So yeah, it will depend on your the P exit will depend on your the exit Mach number. Okay, so currently it will be subsonic, right? So you have
Yes.
A inlet, you have A exit. You can calculate what is the Mach number corresponding to this. A by
Okay.
A star, you have some relation, no?
Hmm. Hmm. Yes.
Yeah,
Yes.
if you know this Mach number at this point, you can calculate what is the Mach number at the exit. So if you
Yes.
know the Mach number at the exit, you can calculate. If you know the pressure at this point, you can calculate the pressure at the exit.
Hmm. Yes.
So now that pressure you have to substitute here, and this is the ambient pressure. So probably whatever you um, okay, so and same thing you have to mention it
No,
here also.
here now, if you can see, for an example, gamma, if you are putting 1.1, for an example, point of view, I'm telling combustion happened, gamma is 1.1 or 1.2, and you put, and here also you can see one P by P naught is there. This
P by
ratio
P
I
naught.
calculated using the Newton-Raphson method. And I got for a constant area ratio, P by P naught always going to be zero. So this part is going to be a constant value. Now in the right side term,
No, it
whatever
will
P by
change.
P.
No, it will change with your as your pressure will increase. Okay, inside the pressure this will increase. Okay, your P exit will change. No.
No, but P by PO ratio
Okay,
always
okay. You are
constant, na?
saying that it is a function of. Okay, let me see. So I see your point. So this is P by P exit. Okay, so which type of this is whatever you are working is the converging type of nozzle, no?
No, converging diverging. It is a like CD nozzle I have designed for the exit point 2 bar.
0.2 bar. This is a P ambient, right?
Yes, I will test it in ambient like 101325 Pascal.
Okay.
Yeah.
Mm, yeah. So okay. So let us see this part. If you have a CD nozzle, so if I assume that the flow is isentropic, so whatever you're getting is just at the initial part, right?
Yes, after like 20, like when I am running my MATLAB code, after 20 step, okay, 20 time step, I am getting, okay, now PC is getting very high. So this right side term is getting low, then I'm getting positive. But initially I'm getting negative.
Hmm.
CF is negative up to some time.
Hmm. But are you so so okay? So yeah, initially it will act like a diffuser, no?
Yes, so that I had doubt. Can I because it is designed for the point 2 bar, can I neglect this entire right side term and only that left side term I will take for my thrust calculation? Is it also a good approximation if I am considering that?
Okay, so
Because it
whatever
is
you're doing
giving.
here now for a initial state when the pressure is not built up and the nozzle is not choked, so this thing will act like a diffuser first of all. Okay, let
Yes,
us consider this. So it will act like a diffuser and the velocity will be lower as compared to this point.
yes,
Okay, so first
yes.
thing is this. Next thing is and but you will be having some higher pressure. P exit will be greater than PA.
Hmm.
Correct,
Yes,
no?
yes.
So you should get this thing as positive.
Mm,
Just consider
no,
this.
PE is less than sorry, PE is less than because my it is designed for the point, point 2 initial, and
No,
I while
that is.
deriving the equation
Mhm.
I have derived on the basis nozzle is choked, then the flow is happening. That initially diffuser thing I have not considered because that is again will make the complication in the derivation, so I assumed
That's
it is
what. So
choked
initially
happened.
you have to consider. That's what I am telling you. I was also so when we were doing this calculation, no. So
Yes,
initially I was getting the negative value in the starting stages. Okay, negative I was getting in. So this point I was not able to get up till this point. Okay,
okay,
so
okay,
but you have to consider this thing. In the starting I told you, right? You have to consider this thing as a subsonic flow.
okay, okay,
Otherwise, you'll not get the correct answer.
okay, okay.
Okay. After that, once the pressure is built up, you can use the whatever you are using.
Hmm. Okay. Okay, so I cannot ignore that right side part. What
No,
I was thinking to ignore that
no,
right hand
no.
side because it is a negative thing is giving.
No. You try to do this, and I so initially I was also getting this thing. So we thought we thought why we are getting these things. Then we realized this is because um, we are not considering the subsonic uh, part. Even if you, I think, have you heard about this open motor? There is tool, right? Uh,
Open motor.
open, I guess open motor. Yeah. Let me check. Probably. Um, Let me share this screen. Share. Okay. Yeah. Yeah. Can you see the screen?
No, I can see the previous screen. Yeah, yeah, it is getting shared. Yeah.
Ah. So there is a you can I think download.
No, sorry, I can't see your screen.
That's what I'm opening. 1 minute.
Yeah, yeah.
So this is a tool that is used to design a rocket engine. This solid rocket motors you can design. So there are different type of propellants that you can use. So say let us use sugar and sucrose rocket, and
Have you shared?
I have shared, right.
No, no, I can't see.
Okay, let me. I think I can. Others can see the screen.
Yes, sir.
Yeah, yeah.
Yes, sir.
Oh, yeah, I can't see. Yeah, yeah, now I can see. Yeah.
Okay, so
Sorry.
these are the different type of grains that we can choose. So let us choose a end burning grain. Okay, and then we have to just write Okay, let us decide a throat diameter. Um, so let us say 1 centimeter. One inch is too much. So this is 0.5 inches. 0.05. Exit diameter. Let us make it as 10. Okay, okay, this is okay, I think 0.5 inch. This is 1 centimeter. Let us make it this thing as 6. um, yeah, expansion ratio is fine. Efficiency, let us not define. Let us define 100. Okay, let us define as one. Divergence half angle. Convergence or divergence is, let us say, 15. uh, so convergence, let us put this thing as 30. Throat length, say 0.1 inch. Okay, 30. 30. Yeah, now it will make sense. No, this length of converging is start. Okay, 1 minute. So this is, yeah, this is the other way around, no? 30, and this looks like a convergent nozzle, no? So okay, apply. Then what you have to do is run some motor, have at least one propellant grain. Okay, so configure maximum level pressure. Okay. Okay. Add grain. Yeah. So the end burning grain diameter, let us say 10, and length, let us make it as 100 inches. Apply. Now let us try to simulate. Yeah. Yeah. So you can see, if I show you only the combustion pressure. So this is only telling you the what is the equilibrium pressure. Okay, so we do not have, so if you have to simulate the entire thing from the transients, right? The
Yes.
okay, so you have to write your own code. You have to see what all so this is what I have shown you here, no? So this code, whatever we have written, so the takes into account for the initial transient. So whatever that code is showing you there, okay, this open motor, this is what we calculate using this p equilibrium, right? When you
Yes.
equate this part. Okay, when you uh, okay, so yeah, so when you equate this generation and the mass that is going out, when you balance this
Yes.
thing, so
Steady
you'll get
state on
equilibrium
time.
pressure, no? So this
Yeah.
code just tells you this part. But if you have to calculate
Yeah,
from
that's
the
steady
basics,
fine.
okay, you have
Hmm.
to calculate from the basics. So you have to it, 1 minute. So you have to write your own code probably. Then you'll get something transients like this. Okay. So yeah. So anything else? Yeah, that's what I was thinking,
Mm.
because initially when we did, we were also getting some negative values. So you can try if you,
Okay.
huh?
Okay.
If you have in
Okay,
doubt,
got it. Hmm.
I'll, I'll help you writing your code.
Yeah, the problem that I'm facing, along with my code, if possible, I will share with you over the mail. Please, if you can, please
Okay,
help.
okay, okay.
Yeah, and also one more doubt I had. The mass you told that it is varying. I have to write. Now, what I was thinking, instead of how the mass is entering into the chamber, I will take the valve as my control volume, I will model there itself. Like in the valve, there is the moment I am giving the signal to open the valve, maybe manually or maybe solenoid electronically, it will take some time to open. So the function by which the valve is opening, like that only my flow will enter into the chamber. So it is the right approach. Through that approach, if I am deriving
Uh,
the equation, how the mass will enter, because now m
Probably.
dot I am thinking is
Uh,
like a constant rate m dot, but now
First of all,
but it
let
is
us
not right.
what you should do is you should allow the mass flow rate going through the engine at a constant mass flow rate, such that you start building up the pressure. Once the pressure is built, you can vary your mass flow rate, so such that you can get your desired thrust values.
No, I think you didn't get.
Huh.
Like when I am opening my valve,
Huh.
it will take some time the valve to be fully open. Like initially, from 0 to 100% opening, the mass accordingly, the amount of orifice opened, that much mass flow will go.
Right.
So with the m dot now, what I am taking is a constant value. So
Hmm.
can I write in the function of that the valve how it is opening, so that it can give a better result? So that way it will
No,
work.
I don't think it will be. It will create such issues. Okay.
Okay.
So yeah, it will not have any significant effect.
Okay, okay. Yeah, that I was asking if it can have significant good result according to experiment. Yeah, I was asking.
Okay, no, no, no.
Okay.
So okay, so I hope any doubts on other doubts.
I don't have. Okay,
Okay,
thank you.
so okay, so with this I'll close the session. So yeah, thank you.
Thank you.
1 second, I have to note. I have to note the email ID. 1 second, please. That works.
Thank you, sir.
Okay, thank you.
Could you please upload the previous week's
Yeah,
videos?
yeah, this I have to
Yes,
do.
sir.
Yeah, I'll do that. Yeah. Okay.
Okay.
Okay. Thank you.
Okay, sir. Thank you, sir.
Uh, uh, Lilandri, Bhushan, right? So,
Yes.
have you noted down?
No, actually, I am not getting where is the message chat box in my screen.
Excuse me, sir.
Yeah.
Hello, sir. Actually, due to my exams, I just missed some classes, sir. I can't
Okay.
able to attend, and
Yeah,
at
I will
week 8
share.
I came.
So, 1 minute. So, maybe I'll share the YouTube link with you all. Okay.
Yes, sir.
So, I've uploaded the.
All videos are there, sir.
Yeah. So,
Uh, I am not getting where is the message.
Either
Can
equal
you
little
type
time.
again so that it will show
Is
me and I can take the screenshot? I am not getting where is the chat menu actually.
okay. So, you're using laptop, right?
No, no, tab.
Tab, huh?
Sir,
So, you should go to this meet, and here you can call messages. I hope it is visible now.
got it, sir.
Bhushan, Bhushan, are you able to see?
Sir, we share the
Yeah, yeah,
YouTube.
yeah, yeah. I take the screenshot. Yeah, thank you so much.
Yeah. Okay. Okay. All the best.
Sir, we
So,
shared the YouTube link, sir.
I have
In that,
shared. Yeah, I've shared this thing.
in this having the all videos, sir, from week 1 to week
This is I've shared
10.
the playlist actually, so you can just
I can just okay.
okay.
Okay, sir. Thank you, sir.
Yeah. Thank you. Okay. So I'll close the session if you do not have any other doubts. Okay. Thank you.
Yeah,
Thank
thank
you.
you.
Thank you.
chill. I
Huh.
wanted to ask which shop in SP Road you had visited
For
for that fittings, bike fittings.
fittings, huh? 1 minute, let me check. Actually, I'm planning to go tomorrow. If you want to go, you can come.
What time will you go?
I don't know, morning only,
What time will the shops open?
10 o'clock.
Sure, huh?
Huh?
Then I'll meet you there directly because it's near. It is on the way to.
Anyway, otherwise, I'll share the shops with you also.
Uh,
Just in case I'm not planning to go, maybe you can just
yeah,
go.
yeah.
Huh?
Just share the name, maybe.
I'll do that. Yeah. Okay.
Actually, this is for the mass flow meter. I'm not able to find NBT connector.
Okay. Okay. Hey, are you using your thermocouples here? The ceramic one?
I'm not using ceramic.
अरे यार, I
You
have to I have to connect them to the metal. यार, I don't have any. I don't know how to do that. So
connect what? Connect ceramic to metal.
metal, हाँ.
I don't know what it means. Ceramic is like what Atanu was using.
Yes, yes.
Oh, okay, I've not at all used.
Okay, okay, no problem, no problem. So I'll share this thing with you. Okay. This.
Okay,
Okay.
okay.
Bye bye. हो गया तेरा? हाँ यार, बहुत पूछते हैं, कुत्ते का महीना है. एक मिनट रुक, एक मिनट रुक.